My name is Pritish Jadhav, and before I jump into tonight's presentation, and which will be on automatic keyword extraction in the context of advertising, I just wanted to give you guys a brief introduction about myself and what I have been up to until now. So, I've completed my master's in science from McGill University with a specialization in systems and control. I was introduced to the world of advertising back in 2015 when I joined a startup called OnlineSales.ai. Over the last 5 years, I have had an opportunity to develop data science projects and products focusing around advertising to help people advertise on the likes of Google, Facebook, Instagram, Amazon, and as well as DNV 360. So it has been an exciting journey until now and many more years to go. I'm basically a generalist who loves building end to end data products, and I'm an absolute fan of using data science stories to make a business impact. Over the past 1 year, I have been associated with Perpetua as a data science engineer. Perpetua is basically a software first advertising company. We are on a mission to give superpowers to anyone who sells online. I'm currently associated with the Machina squad, which is responsible for building algorithms that powers Perpetua's core engine. So all the data science stuff, all the ML stuff that goes into the engine. Uh, it has been an exciting 1 year for me. I was literally the 18th or the 19th member to join the squad, but we have grown over 50 people over the last year, and it is amazing. Let's get down to the topic for tonight, which is the automatic keyword extraction. Uh, this is no headlines, but the pandemic has affected all of us over the last 1 year. The nationwide lockdowns and social distancing protocols have definitely changed the way we interact in the society. It has also impacted businesses worldwide, especially the ones who rely heavily on foot traffic for driving their sales. Having said that, e commerce has grown by leaps and bounds. As per the data collected by Bank of America, uh, the US e-commerce penetration has increased from 16% in 2019 to 27% in by April 2020. That's a whooping 10x growth over the last 10 years, which is pretty amazing and exciting. This may not be a good example, but just to give you guys a directional sense of how things have been shaping up, the market capitalization for Amazon has increased by $570 billion over the last 1 year, and it currently stands at roughly $1.49 trillion. Across the border, Shopify is now the most valued company in all of Canada, and it took over the heavyweight RBC Bank sometime mid last year, if I'm not wrong. But yeah, hopefully that gives you guys an idea how the things have been changing across e-commerce. Having said that, building an online presence is not trivial at all. It involves building a website, building mobile apps, branding, content creation, advertising, marketing. And I'm pretty sure there are various other bits that I have missed out on this slide. And I can vouch that each one of these bits are 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 pretty intrinsic and not trivial at all, and it takes years to perfect them. But tonight, I was hoping to kind of focus on one aspect of it, and that's advertising. On this slide, I have a bunch of heavyweight brands listed out, including Google, Facebooks of the world. Uh, Even though these guys have their consumers spread across the world, there's a common link between all of these businesses, and that's sponsored ads. All of these brands and logos rely heavily on advertising for driving their revenues. Now, there's this broad concept of classifying advertising into two categories, and that's push advertising, and then there's the pull advertising. Pull advertising is the one where the users don't specify their interests explicitly. Imagine browsing on Facebook or going through your feed on Instagram, and you get some ads hit up on you. These are basically the ads that are triggered based on your implicit feedback or based on the notion of impulse buying. On the other hand, there's the likes of Google and Amazon who rely on explicit intent on the end of users to serve relevant content. So you go onto Google or Amazon, search for a product you have mentioned or intend to buy. That helps these guys to figure out the right content to show you, and that's how the ads are served on those platforms. So yeah, if you can see the left hand side of my screen is basically all the logos that use pull advertising, and the likes of Facebook using push advertising. Tonight we are specifically gonna focus on the pull advertising aspect of things. So before we jump into the data science stuff, what really happens when you search for something online? So imagine I'm searching for red shoes on Amazon, and as soon as I hit the search button, there's gonna be a real-time backend auction that is conducted by Amazon. And like any other auction, whoever bids the highest gets their content shown. But then the question is, who are these bidders? These bidders are basically the sellers and brands who want to show their ads to their end users. As soon as the bid auction results are declared, the content is rendered on its platform. And make no mistake, this happens like literally in microseconds. So you don't even have to. There's not an elaborate auction that goes on in the backend. It's pretty fast, and it's all computerized and programmatic. So once the results are shown, they are blended in with the organic search results. So the users may not notice the difference between organic listing, but as an end user, you would go through all the product listings, browse for the product that seems interesting to you, perhaps add to cart at some point, and then buy it. And then once you buy the product, it's the time to celebrate for the seller or the brand. That's when an actual revenue gets tied to the click that happened early into the funnel. Uh, and yeah, that's why I call this as a funnel, because there's no instant gratification in advertising. And if you think about it, at each step of this process, there are a few number of people that would drop off. So imagine Amazon serving 1,000 impressions to the people out there. Perhaps 100 people out of them would click on it, 10 people would add to cart, and then ultimately one person would buy it. So uh, it kind of mimics the behavior of a funnel. And like every other funnel, you can optimize at each and every step, uh, and have sophisticated data science and ML products to kind of gain maximum out of each step. But tonight, we are going to focus on the top of the funnel problem. Imagine you are starting out with an advertising campaign on Amazon or Google. The first question that you want to answer is, what kind of keyword should I be bidding on? Because there are like literally infinite keywords that would be relevant to your products, but you may not always know where to get started with. As it currently stands, most of the process is pretty manual, and it involves a lot of research and trend analysis. Even worse, it's subjective, because you would do this process repetitively, and you'll have to come up with keywords every single time. So it's very, very difficult to replicate your success across the board. And this may even be fine when if you're dealing with like 15, 20 products in your catalog. But as soon as the product catalog size increases to, let's say, 1,000 or tens of thousands of products, this can get pretty out of hand. And that's why businesses out there need a more robust and a scalable solution. And that's where the data science kind of comes into the picture. So, with all the context set, let's get down to the actual algorithm. Just to reiterate the problem statement, we still want to extract the keywords that we can use for advertising on any of the pull advertising channels, including Google, Facebook, Target, Walmart, whatever it may be. So, the broad algorithm can be split out into 5 different steps, and that's data cleaning, uh, noun phrase extraction, page rank algorithm, the rank ordering of those noun phrases, and then launching a campaign. Now we will get into all of these bits in varying degrees of detail, but before we do that, let's look at the live demo, because I believe that's something that would set the tone for all the mathematics that's going to come from here on. So I have this quick Jupyter notebook kind of uh, set up here. All I'm going to do is I'm just going to run all the cells, and wait for it to show its magic. While it's doing that, it's going to take quite some time. Let me walk you guys through the broad algorithm. So what we have at the input is basically access to a product catalog for a client, and I've downloaded this data from Kaggle, which is basically a product catalog for, I don't know, for some few categories, so it's manageable. But you can see that there are a few titles here to go with, and they have all of them have a unique ID, which Amazon kind of uses to track activities. And then you have a bunch of Python code. I won't really go a lot into its details, uh, but yeah, yeah. As the slide lists out, the steps can be broadly classified into data cleaning, noun phrase extraction, the page rank algorithm, and then rank ordering them. Awesome. Uh, we will discuss all of this in detail, but just check out the results. So, given the titles and the product descriptions, the algorithm was able to kind of extract keywords automatically that are pretty good to get started with. So, if you're someone who's getting started with advertising and that's your product catalog, these keywords look pretty good to me. Board games kits. You have heart horse toy set, wooden music toy set. That's really good. So you have these keywords and you have a normalized score for each one of them, and I've rank ordered them. So you can always choose the number of keywords that you want to go live with and launch your campaign. With that in mind, let's get back to the mathematical details. So as I said, the first step after loading the product catalog is to clean your data. For this particular application, I have done very basic data cleaning that includes cleaning out the punctuations, handling special characters, converting everything to lower cases. Now, I've not specifically done this, but based on your application and how you want to go about doing things, you could leverage stemming and lemmatization as well. This is one of the most boring things to do as far as data science is concerned, but I truly believe that it yields rich dividends as when you think about the grand scheme of things. The next step is actually the noun phrase extraction, and this is where things start to get interesting. If you hit up text rank or page rank on Google, this step would be slightly different, and no one really does this. But since we are working on advertising kind of a text, it makes sense to extract them because whenever we search for something on the likes of Google or Amazon, we typically search using noun phrases: blue jeans, black shirt, red shoes, right? So these are all noun phrases. So it would only make sense to kind of extract them in advance and then leverage something like a page rank algorithm to just rank order them. I have a regex chunking expression listed out there, but I'm pretty sure that it's just the part of speech tagging problem is kind of a solved one. And there are a lot of tools out there, including NLTK, that you can leverage to extract part of speeches from your text. Um, a quick mention that it may not be as trivial for non-English languages, but I would encourage you to find more libraries out there that can help you solve it. Once the noun phrases are extracted, the next step and the heart of this algorithm is the page rank algorithm. And we're going to spend quite some time on this one. It was first introduced by Google for ranking their web pages. So in the beginning, Google started out their search engine, and they still needed a way to kind of rank order the web pages that it was kind of indexing. And that's when Larry Page, one of the co-founders of Google, invented the algorithm. So contrary to the popular belief, the algorithm is actually named after its co-founder and not after its application. So what really is an PageRank algorithm? A PageRank algorithm is basically a graphical model with web pages as the nodes and the web links on it as edges. So how can we render this core algorithm for our use case where we would want to rank our noun phrases? We would want to replace the web pages with text as nodes and then add edges between words that go occur within a range of n words. And a typical example would be a bigram or even a skipgram. but you can get pretty inventive with this stuff. And there are a lot of interesting research papers out there who have leveraged interesting graphical modeling techniques to extract something that is not trivial. But if you look under the hood for the PageRank algorithm, it's essentially a Markov chain model. A Markov chain is basically a mathematical model for describing a sequence of stochastic events. So the events in our day-to-day life are not deterministic. There is a stochastic nature to it. And modeling such a sequence, typically people fall back to Markov chains. So this is like a small screenshot of a two-state Markov chain. You have two states, A and B. In our case, this would be two tokens, say red and shoes. And with certain probability, you can transition from state A to state B and vice versa. However, like working with these graphs, it can get pretty tricky. So we need some way to represent them mathematically. And that's where the transition matrix kind of comes into the picture. So for a Markov chain, you have a transition matrix with the current state and the next state, and for each from each of the nodes you there's a certain probability that you can transition from that state to some other state. It is important to note that the transition matrix that I have here is a column structure. What do I mean by column structure? Basically that all the columns of this matrix would add up to one. And this kind of makes sense because at the end of the day, we have probabilities in here, and probabilities should add up to one. So you can see here the probability of me staying at node A, uh, if my current state is A, is 0.54, and the probability of me migrating from A to B would be 0.46. Both of them add up to 1. The last bit of information that we need before we jump into the weeds of the algorithm is how to compute the state probabilities at any point in time. So let's take a step back and make a note that this is basically a model that is sequencing in time. So for each point in time, you would have a probability vector. So the state probabilities at time k can be given by a into xk minus 1, where xk minus 1 is basically the state probabilities at time step k minus 1, and a is the transition matrix that we have already defined above. Now, if you want to know the state vector at any time k, you would just recursively substitute the values of xk minus 1, and you would get xk is equal to a raised to k into x0, where x0 is basically the initial state probabilities. And you can get as innovative as you want, but uh, initializing that to a uniform distribution would not be such a bad idea. So yeah, I think we have all the basic building blocks for the PageRank algorithm, as well as what do I mean by the Markov chain. The next part in the PageRank algorithm, and that's the part that we saw in the demo as well, is training the PageRank algorithm. What do I mean by training a PageRank algorithm? Once we have the transition metrics, we would want to know the steady state probabilities. And steady state probabilities are basically given a transition matrix A, we would want to know the long-term probabilities of the system being in each state. So if I keep running the system for, let's say, time equals to infinity, how would the state vectors look like? And that's what we would want to compute. So how do we compute this steady state probabilities? As I mentioned earlier, computing steady state probabilities is basically we want to find a vector x infinity such that at time step infinity, such that a into x infinity is equal to x infinity. So applying the transition metrics to the state vectors does not have any impact on that. Now, if you think about this and take a step back, this is something that you may have encountered at some point in your life. This is awfully similar to the definition of eigenvalues and eigenvectors. The mathematical formula for eigenvalues and eigenvectors is ax is equal to lambda x, which basically means that eigenvector x is something that whose direction does not change even after applying a linear transformation a, And in other words, the linear transformation A on a vector X can be completely captured by a constant lambda, such that X is the eigenvector and lambda is the eigenvalue. So now if we substitute the eigenvalue to be 1, we get a very similar expression that we have defined for the steady state probabilities. So the problem of computing steady state probabilities ultimately boils down to computing the eigenvectors for eigenvalue equals to 1. The pressing question at this point is, would we always have an eigenvalue equals to 1 for the transition matrix? And the answer turns out to be yes, because we are dealing with column stochastic matrices, and due to some brilliant mathematician, we already have a proof that states that a column stochastic matrix would always have an eigenvalue equals to 1. So that is pretty important, and I would highly encourage you guys to check out the proof for it if you are super interested in it. But yeah, we now know how to compute the steady state probabilities of a page rank or a graphical model or a Markov chain. Right. Once we have trained the PageRank algorithm, we would know the steady state probabilities for each of the tokens in our graphical model. And the perhaps the last or the second last step in our process would be to take the steady state probabilities. So you have the steady state probabilities for each of the tokens, set, toy, party, costume, all of it. And know that adding up all the steady state probabilities, they would add up to 1 because we are dealing with probabilities again. And you have your noun phrases that we extracted from step number 2. Come up with any form of aggregation function to kind of merge this in. For this application, I've just used a simple addition, and there are a number of drawbacks to that, but I wanted to keep things simple. You compute the final scores by kind of using the steady state probabilities, and what you get at the output is what we saw on the Jupyter notebook. Key phrases with the score and their phrase length. And these are the set of keywords that you would want to go live with for your advertising campaign. And these are basically the same set of keywords that we saw in the Jupyter notebook, and they are pretty promising. Uh, so yeah, the last step is to take these keywords and launch them on your choice of full advertising platform. It may be Amazon, it may be Google, it may be Walmart, it may be Instacart, any of it, and then watch your sales grow. Amazing. So that was the entire algorithm. Before we wrap up this presentation, I just wanted to take a couple of minutes to highlight the limitations of this algorithm. Uh, we have essentially made an assumption of ergodicity for the Markov chains. Ergodic Markov chains are basically the ones where it is possible to jump from every node to every other node in your system. And this does not have to be on the initial time step. It can happen at some point in time, but there has to be a way for you to reach from point A to point B in your system. If you think about text or even web pages, this assumption can fail pretty easily. You can have a lot of dead links in your while working with your text or even on your website. So this is actually a solved problem, and that is resolved by using the concept of teleportation. And what teleportation essentially means is if you get stuck on a dead end, uh, you just randomly transit to any other state in your system. So there's not a lot to it, but it solves a very important mathematical problem. The other limitation of this approach is, again, it's in the name, it's an extractive process. It's not a generative process. So we are not leveraging any kind of generative model. Although I would like to highlight here that the same concept, the same Markov chains can be used for generation as well and not for extraction. But that's perhaps a topic for another day. So yeah, it's extractive, and it leverages a lot of your underlying pattern in your product titles and descriptions to extract the right set of keywords. And by its extension, it becomes a garbage in, garbage out kind of a model. So if there are a lot of issues with your product titles and descriptions, you're probably not going to get anywhere. And then the third and the last limitation, well, maybe not the last. There are a bunch of other limitations that we can dig out, but this is one of the prominent ones, and that is the evaluation metric. Throughout this process, you may have noticed that I did not use any kind of evaluation metric to decide whether the extracted keywords were good enough. And that's because we are essentially working on unsupervised principles, and uh, it can be difficult to evaluate your algorithms when you are working in an unsupervised kind of a setting. This is just one of the problems that we are tackling at Perpetua, and I've been actually working on it for quite some time. And as I mentioned earlier, there are different problems on the funnel.
How do Markov chain model sponsored advertisements in e-commerce? Sorry, I'm struggling to make the macroscopic connection between the two major themes in your
So yeah,
presentation.
as I mentioned, the entire problem of advertising can be visualized as kind of a funnel. But as I mentioned earlier, in this presentation, I was kind of focusing only on top of the funnel problem, and that's identifying the keywords that you would want to bid on. So as an advertiser, or as a brand out there who is getting started with advertising, you would still want to kind of identify the keywords that your ad should kind of trigger when people are searching for it. And that's how Markov chains kind of come into the picture. It's a mathematical model for sequencing, for modeling your sequences. And as you can imagine, the text is basically can be visualized as a sequence.
When constructing the graph for PageRank, do you use the words as vertices? And
Oh
what
yeah,
are the
so
edges?
definitely, you are absolutely bang on. The words are being used as vertices, and the edges could be directed or undirected. So I've kept it undirected for this kind of demonstration, where I've just extracted the bigrams or the skip grams from the product titles. And so if you have a bigram, let's say red shoes, I would add an edge between red and shoes, and that's how I connect an entire graph out of it. Although there are different researchers out there that have leveraged the likes of TF-IDF or any other metric to kind of gauge how closely two words are connected with each other. So you can actually build out a directed graph and then train the same PageRank algorithm where it's basically about computing the steady state probabilities.
Is the Makarov chain still competitive? I know some people use NLP to extract a feature from the search and find the nearest neighborhood from the database.
Yeah, so there are a lot of extractive algorithms out there, including the nearest neighbors ones. But I've used this earlier, and I think this is pretty competitive out there because it's not generative, but you want to do a good job of extracting text, and it has solved the purposes in the past. But yeah, feel free to kind of experiment with all the algorithms out there.
I'm new to retail and e-commerce. Is there any good online resources to catch the trend of data science in retail and
Um,
e-commerce? So maybe asking about kind of good online resources that you
Yeah,
might know
definitely.
of there,
Like before you
Pritish.
get started with like data sciencey and the machine learning stuff, I would definitely recommend you to check out how advertising in general works. And you don't even have to go anywhere. So I know for a fact that Amazon, Google, even Facebook have a lot of resource where the courses are open sourced and free for you to figure out how Google advertising works, how Facebook advertising works. And to be honest, the underlying principles of advertising remain pretty much the same across the board. So before you start with the data science, I would highly encourage you to check out those materials presented by Google, and then work your way through it.